Hi, I'm Steve Ward, and in this technical session I'm going to talk about industrial motors and variable frequency drives. Industrial motors are extremely common in industrial applications. They're used for driving conveyors, they're used for pumping, they're used in machine tools, they're used for driving fans, they're used for drive mixers, and a variety of other applications. The most common are AC induction motors. AC induction motors are robust, relatively inexpensive, and require little maintenance. The way an AC induction motor works is it uses electromagnetism to spin a rotor inside a stator. They're very well suited for constant speed applications, and the speed is based on the frequency of the electrical input to the motor. If you need variable speed, and also for some motors we also like VFDs for speed control and for eliminating electrical noise and improving efficiency, but the VFD can be used to vary the speed of the AC induction motor and drive it at different speeds under different conditions. There are other motor types. DC motors, these use permanent magnets. They have a high starting torque and good speed control, and there are different types of DC motors. Common types are brushed and brushless, and the thing about DC motor is the speed is proportional to the voltage, so by changing the voltage you can change the speed. We also have linear motors. Linear motors are based on other motor technologies, but instead of being in a circular arrangement, they are effectively folded out so that the device that's being driven can be pushed to one end or the other end, or controlled somewhere along the line of the linear motor. So it's the same sort of technology, but just laid out in a flat arrangement rather than a circular arrangement. AC synchronous motors, these are motors that rotate exactly in sync with their power frequency, which is very useful when fixed speed operation is critical. They have a low power factor and high inrush current, so those are disadvantages, although you could use an AC synchronous motor alongside other motors to improve the overall power factor by offsetting other types of energy systems, but the high inrush current is still a disadvantage. Servo motors are generally smaller motors which are very accurate and quickly respond to controlled signals. These are normally used on machine tools and other machines which need precise positioning. And then we have stepper motors. Stepper motors are relatively smaller again and also lower cost. These move in discrete steps, which enables precise motion control, this time without any feedback sensors. So they're open loop and it makes them simple and less expensive than servos, but they need to be sized properly and they need specific electronics to control them, and there is a possibility that if the load is too high they won't move and then you'll have no feedback that they didn't move, and that can affect the overall accuracy. Also, stepper motors have good torque characteristics, but the key point is for small applications where cost is an issue. So the most common type of motor is a three-phase induction motor using a squirrel cage. So the squirrel cage is effectively a set of copper or aluminium bars, and they are shorted by end rings, and then outside of those we have stator windings which are on the outside and fixed into the motor. When you feed in an AC current to the stator, it causes a current flow in the stator without any brushes required. And then the rotating magnetic fields, they're caused by the current, and that drives the motor through electromagnetic effects. Now, three-phase induction motors are asynchronous. The speed is slightly below the supply frequency by between 0.5 and 5%, so there's an accuracy issue here. But in many applications, 0.5 to 5% is not a problem. One nice thing is they are self-starting. As soon as you apply a current, this causes electromagnetism that leads to motion, so you don't need any specific starting techniques. A downside is you do get high current if you use direct online. Direct online is where you apply electricity directly onto the motor via a contactor with no other mechanisms. The high current, that can be offset by using other methods such as a VFD or a soft starter, or there's also a possibility to use older techniques by using star and delta type starters, which can reduce the initial high starting current. Now, most industrial motors are three-phase motors. One phase is a possibility where you have a single conductor or a single live component and the neutral. And in this case, the electrons flow from the live through the load and into the neutral. Very simple, only requires 2 cables, but you'd probably also need a safety earth. But these need potentially high power circuits. Because you've only got one phase, you need large cross-sectional area cables in order to carry the high power. So in larger power applications, we use 3 phases. In this case, you get 3 conductors, 3 lives. There is sometimes a neutral, but not always. You'd also need a safety earth as well. But the idea now is that 3 phases are offset from each other, and each phase is carrying a different alternating current offset from a percentage by the other different phases. So this just requires a bit of extra hardware in terms of the motor and in terms of the generator, but it allows us to have a simpler circuit without having to have huge cross-sectional areas that we might need with a single phase circuit. Electrons flow between the live conductors, and the idea is that as you've got this offset alternating current, at any one point you'll have a higher potential at one point moving to a lower potential at a different point. If it's a balanced circuit, which is often the case in a motor, all the 3 phases are identical, then there's no current flow in the neutral, so that's why the neutral is optional. But in some applications there might be an unbalanced flow and you might get current flow in the neutral, so sometimes neutral is used, and we'll see how that applies later. So I mentioned star-delta connections. Star-delta can be used for starting up. It can also be used as a way of balancing an unbalanced system by providing a neutral. So in a delta system, we have effectively like a triangle type circuit where each coil or each component is connected across 2 of the live circuits. So you'll have one side that's connected across live 1 and live 2, another side that's connected between live 2 and live 3, and the final side is connected between live 3 and live 1. Now in this case it's a balanced circuit, so you don't need a neutral, and the components are driven by the alternating currents as they differ between the live 1, live 2 and live 3 due to the phase ranges. The alternative is a star arrangement where there is a central neutral point, and in this case the 3 components, one component is connected between live 1 and neutral, the other component is designed to connect between live 2 and neutral, and the final component that's connected between line 3 and neutral. So the rated voltage for a star connection is higher than for a delta connection, so you need a higher voltage, but a higher voltage can also mean lower current, so you might have a star-delta starter where you connect via a star first to bring the motor up to speed, and then you swap over to delta operation for when it's finally running. And then you can also have a motor that can run of different voltages. That can also mean that that single motor can be used across different applications as well. So you might have a 240 volt delta or 415 volt star. If you're connecting to a VFD, then normally the VFD will tell you which mode of operation to connect. Typically that's a delta connection. But yeah, the idea of star and delta, it just gives you more flexibility in starting for certainly for larger motors, and the possibility of running at different voltages depending on what the motor ratings are. Now we have the concept of wound rotor motors and slip rings. In a typical 3-phase induction motor with round rotors, there's an equal number of wire wound rotor poles and stator poles. Between these you might have slip rings. These are used to provide a means of inserting resistance for starting and varying speed. So this is an old sort of electromechanical mechanism of changing the motor speed, and the rotor windings themselves, they would be connected via external resistors. So what you would do is you would adjust the resistance, allowing control of the speed and torque of the motor. So we don't often see this today. This has been superseded by squirrel cage designs and variable frequency drives, which give us that speed control, but you may occasionally come across these in legacy type applications. So when we consider a motor, there are various parameters that are important. First of all is voltage. Typically, at least in Europe, this is 415 volt AC, which is a standard voltage provided from 3-phase incomings to factories. Can also be provided via transformers, which can convert down from much higher voltages depending on what the factory input is. Current to the motor, that depends upon its motor size and load. And of course, when the motor is running at full speed, it will run at full current. Phases, usually there are 3 phases. This gives us the most efficiency of the motor without having to need very large conductor sizes inside the motor. Frame size, that's the actual size of the motor, and there are standardized frame sizes for particular applications. And then there's speed. Speed is conformed by driving the AC motor at its rated frequency, and that will cause it to rotate at its rated speed. So if we have 50 Hertz common in Europe or 60 Hertz in America, depending on the motor and country of use, those speeds will cause the AC motor to operate at its required speed. Now, the rated speed isn't necessarily the maximum speed. We can go faster than the rated speed, but if you go too fast, then you do run the risk of damaging the motor, because you've got rotational forces that can cause the motor to expand internally, and potentially that could be catastrophic, or as a minimum it could lead to damage to the insulation or the windings, which would prevent the motor from operating or damage it in terms of not being able to operate at its full speed. So we can operate it up to about 125% faster than the rated speed, but above that is not recommended. Now, there are other motor factors that might be important. Of course, there might be cost, there might be weight, which are important when we're purchasing the motor and moving the motor. But in terms of control parameters, voltage, current and speed are often the important ones. Phases, of course, normally it's 3-phase, so we don't have to worry about that too much. We might also worry about kilowatts. Kilowatts is related to voltage and current and can be used to size the motor. Smaller motors might be in watts, but typically it's more the current we're concerned about. Voltage is normally the same, normally 3 phases, so it's the variable current which describes what we need to do in terms of controlling that motor with our control equipment. So the issue with a motor is, if you try and start the motor direct online by attaching it directly to the mains using typically a contactor, there would be a large inflow current as the motor starts to run. That can cause damage to the electronics, it can cause problems with the inflow to the motor, which means we need to oversize the rest of the plant. It can mean large fluctuations in power, it can affect other equipment nearby. So often what we do, particularly with anything from 750 watts and larger, a modern approach would either to be use a soft start or a variable frequency drive. Now, soft starts and variable frequency drives, they're actually the same technology. The difference is a soft start has a fixed speed, where a variable frequency drive has a variable speed. But inside, they're pretty much identical in terms of the way they're arranged. Just the variable frequency drive has a few more components for the variability part of it. So variable frequency drive, or VFD, they're also known as variable speed drives. They're known as inverters. Sometimes they're just known as drives. What a VFD is, it's a combination of power electronics, and that allows the magnitude of current and voltage to the motor to be controlled. So the first thing we can do is we can control the starting current and voltage. They can be increased at 0 or low speed to increase starting torque. Alternatively, they could be reduced to reduce the overload on the rest of the system. But the amount of starting current and voltage, that would affect how much of a load you can control, and it would also affect how long it takes to spin the motor up to speed. But the idea is, by adjusting the voltage and current, and ultimately by adjusting the frequency, this allows us to control our motor very accurately. Now, VFDs often have additional technology in them to have startup and deceleration and acceleration ramping, so we can also control the acceleration and deceleration. Now, ultimately, that will be controlled by physics. You can't accelerate faster than the torque of the motor can deliver to the actual mechanical equipment that's fitted. But you often want to accelerate slower than that, because you don't want to damage the mechanics. You want to avoid stresses on the gearbox and to any other mechanical components fitted. So often it's desirable to have a slower acceleration than is actually possible. And that's something else that a VFD can handle. And we can also handle a slower deceleration. Rather than just removing power and letting the device coast to a stop, we can have an active controlled deceleration, which can be faster or slower than if we just left the hardware to decelerate by itself. The key point is that VFDs, as well as controlling the speed, they can also save energy as well. So we optimize the current and the voltage to the motor, we optimize the frequency to the motor, and as a result of that we have control of the motor and we have the potential for energy savings. It also increases the life of the equipment as well, because we're reducing the mechanical shock, particularly by accelerating and decelerating more slowly than just by direct online techniques. That can allow us to minimize the hardware shock when we start or stop the motor each time, and that can extend the life of the equipment as well. So how does a VFD work? Well, we start off by having an AC supply coming in at a fixed frequency into the variable frequency drive itself. This AC supply comes from our main supply, and that's normally fixed by the power generator. Typically in Europe, as I say, that's 50 Hertz, plus or minus maybe half a Hertz or less. In the USA, you might see 60 Hertz. In other countries, they would typically use 50 or 60 Hertz, depending on the country. So we feed the AC supply into the VFD and we convert it into DC. So now we have a direct current voltage. And then what we do is we take that DC voltage and we chop it up and convert it into a pseudo AC sine wave at the required frequency. So what this means is we can have 50 or 60 Hertz coming in, and then we can control exactly what the output frequency is, starting at 0 and then ramping up to the maximum frequency of whatever the motor can take. As I mentioned, typically that's 125% of the rated speed, which means 125% of the typical rated frequency. Now inside the VFD, we have various electronics to control the AC frequency output. That includes controlling the speed, it includes controlling the ramp up, the ramp down, and then there may be advanced functions including encoder feedback for more accurate control. By using an encoder, we can actually eliminate that 0.5 to 5% drift and make sure we're controlling it exactly. We may have PID control, so we can follow a set point input and then accurately provide an output to control a process variable. We can perform vector control, which is a way of handling the motor dynamics more accurately, again to reduce energy usage and to improve motor performance. We can also handle safety via techniques like safe torque off to allow us to shut down the motor in a safe way. So there's multiple things that the VFD electronics can do in addition to just controlling the motor speed. Key benefits for the VFD include soft start and controlled stop, which, as I mentioned, reduces mechanical wear and reduces the startup current. We have the variable speed control of the motor. We have power savings. Normally these don't apply to very small motors because the power savings are very small, but as the motor gets larger, a small power saving can make a bigger difference. And there's a European Union regulation, unless you've got a very special type of motor which has very high efficiency, then a standard motor, the European Union regulation says you do need a VFD in order to control that 750 watt or above motor and get the best power savings from it. VFDs can also give us diagnostics. There's lots of feedback about what the motor is doing, what the actual frequency is, what the actual voltage and current is. Particularly important for energy saving is kilowatts and kilowatt hours. And of course, we can look at things like power factor as well. And then there may be other feedback depending on what the VFD gives us. And then there's all these advanced control capabilities without extra components. So for example, a PID controller inside the VFD, that could eliminate the requirement for a separate PLC and reduce the amount of hardware you need to do closed loop control. So there's several frequencies that apply when you control a VFD. First of all, there's the frequency of the recreated AC output. This is the actual frequency which causes the motor to rotate at whatever its rated or desired speed is. So we mentioned this, typically it's 50 or 60 Hertz depending on the motor and the country of use. Can be up to 125% faster, but typically no more than that or the motor would be physically damaged. So 50 Hertz times 125, that's about 60 Hertz. 60 Hertz times 125, you're approaching up to probably not more than 75 Hertz. But the idea is, we can drive the frequency of that recreated output according to what's required to drive the motor from 0 speed all the way up to its maximum speed for the application. Now, on top of the recreated AC output, there's also a switching frequency for the DC to AC conversion. This needs to be high enough to produce a reasonable AC waveform, So we can't just have a system going on or off at 50 or 60 hertz. It would need to be faster than that. But what you could also do is you could have a faster frequency, but if it's too fast, then you start getting harmonics in the motor windings, and that can cause higher frequency losses. So you need to have a suitable switching frequency between the two. Typically that's 4 kilohertz. But that can lead to audible noise, which can be annoying in some applications, particularly in consumer type applications, maybe where you're driving a lift and you've got a lift hoist motor. If there's a 4 kilohertz noise, yeah, that's a high frequency noise which people can hear, and that could be very irritating. So sometimes you might want a higher frequency so that you still get your good AC waveform, but you don't get that 4 kilohertz. But normally 4 kilohertz is about the optimum, because any higher than that and you do get losses in the motor windings due to harmonics. Now the VFD is an electrical device, so it needs an electrical connection, and there are two sides to the electrical connection. There's the mains connection and then there's the motor connection. So on the main side we have the incoming supply. It is possible to feed the VFD with single phase, but most VFDs would be supplied with a 3-phase input. So we have live 1, live 2 and live 3, or for 2-phase there would be live 1 and neutral. There's also a protective earth. On the incomer to the system we typically have some sort of disconnect method, and normally that is just for maintenance purposes. We don't disconnect the VFD unless the motor is stopped. That's just for disconnecting for maintenance, the disconnect from the main supply. There would then be fuses or a circuit breaker, so they would be at or above the current that we were expecting for the VFD to consume based on the motor size. We may have a line reactor or a choke, and we may also have an external EMC filter. Some modern VFDs have a built-in EMC filter, but there may need to be additional EMC, and there's also a line reactor and a choke. They're additional devices which you use for protection and also for smoothing the voltages. I'll come on to those later. On the motor side, then we have a 3-phase supply to the motor. Again, typically it's balanced, so we only have the line 1, line 2 and line 3, but it's renamed as UVW to avoid disconnecting the motor or connecting the motor incorrectly. You then may have an output filter or choke. Again, that's optional, but it can be used to smooth the voltages and controlling the wiring. There may be an optional brake resistor. The brake resistor is used to dissipate some of the energy when the VFD is slowing down the motor. There may be an optional DC input. This can be used to keep the VFD powered on the electronic side even when it's disconnected from the mains connection. And then there will be the motor cable with possibly a protective earth and shielding, but not necessarily. It depends on what the arrangement for the motor is, how long that cable is, and what sort of protection and harmonics and interference you're prepared to put up with, and also maybe what sort of supply you're expecting in terms of the environment and the initial power coming into the module. Now, for safety reasons, no control components are recommended between the VFD and the motor. If you were to suddenly disconnect the motor while the VFD was running, that can cause severe damage to the VFD and destroy it. You are allowed to have a service disconnect, but the motor must be stopped and the VFD must be powered down before use. The reason for the optional connections is to allow additional functionality. So we start with an external line reactor. This is recommended when the incoming supply impedance is very low or the short circuit current is high. So what this does is the line reactor actually limits the amount of energy coming into the VFD under a fault condition and could prevent damage to the VFD and also help from a safety point of view. It can also be used to balance out supply dips. So if the supply is prone to dipping occasionally, a line reactor can overcome that. Can also be used to help balance an unbalanced 3-phase supply, typically where voltage variance levels exceed 3%. It can also help where the VFD is supplied via a bus bar and you have a brush gear system. This is common in rotating systems and linear gantry type systems like overhead cranes. So the idea of an external line reactor on the incoming side is it's just to smooth in the incoming voltage to the VFD. An EMC filter is also optional. That reduces the transmission of noise back from the VFD to the supply. And the reason for that is, we've got these complicated power electronics running at high frequencies, and they create harmonics. Some of those harmonics could be fed back into the supply, so having that external EMC filter can minimize the amount of those harmonics and the transmission of that noise. The DC input I mentioned, that keeps the VFD powered when the supply is removed. So helpful if you want to maybe set up the VFD parameters when the VFD is powered down, but you still want to do work on it. It can also be used for diagnostic purposes. As I mentioned, no switch gears allowed between the VFD and the motor. For the European Union, for EMC compliance, we normally need a screened motor cable. So that reduces the transmission of noise from the motor wires out to the outside world. And then the final thing we might need is an external output filter or choke. This is recommended for motors that aren't suitable for use with VFDs. Most modern motors would be suitable, but some motors aren't. So an output filter or choke, what it does is it smooths up that chopped AC voltage and turns it into a voltage which is a bit more smoother in terms of its AC capabilities or its AC waveform. We also might use an output filter or choke to allow longer cable distances. And also, if you've got high capacitance motor cables, then the filter or choke, that can be used to offset the capacitance and still allow those cables to be used. Now, when the VFD is turned off or slowed down, the motor continues to run and it continues to be controlled by its load. That load could be significant. What happens is, as the motor slows down, then there is power that's generated by the motor because the motor turns into a generator. Now, what you could do is you could just let the system coast to a stop at whatever speed it takes to take. But that could be some time. If you've got a very high inertia load, for example, you might have a big rotating piece of machinery, or you might have a conveyor that's loaded with lots of devices, whatever they need to be. I remember working in a quarry where we were using conveyors to transport rocks, and those rocks could have a very high inertia. So you might stop the conveyor and it might slow down and take several seconds or tens of seconds or potentially even minutes to actually slow down. So there's a couple of options we've got here. What we can do is we can regenerate the electricity. So this involves reforming the generated power and sending it back onto the supply. So you probably experience this if you've ever been in a modern car, particularly an electric car. What happens is when you take your foot off the accelerator, then we use regeneration to take that inertia of the vehicle, convert the alternator of the vehicle or the electric motor of the electric car, and then we turn that into energy that can be fed back into the battery to recharge the battery. So it improves efficiency, and it means that you don't have to charge your car up as often. And in smaller cars, particularly hybrid cars and those with the simpler systems, again, it just means that the battery is charged up from regeneration rather than having to use power from the main motor. So that's one way of doing it. But it does involve additional electronics. Those additional electronics, they're needed to effectively turn the VFD back to front. So instead of supplying power from the mains to the motor, the VFD now has to supply motor power back into the mains. So often that involves a parallel set of electronics. So we're effectively doubling the cost. And then there's additional electronics which are required to match the frequency of the supply. We can't just put AC voltage onto the supply. We've got to match the frequency of that supply. Otherwise, we could seriously affect it. So regeneration is good, but it means that you have to pay a lot more for your VFD. So an alternative option is to use a brake resistor, and we take the generated power from the motor and the load, and we turn it into heat, which we can then dissipate. So taking that heat, that heat has to go somewhere, just goes into the atmosphere, but it's a cheaper way of improving the performance of the machine when it slows down, and by eliminating all of the extra energy and making it sure it slows down. Another option, of course, is to use a mechanical brake, but if we use a mechanical brake, then again we've got extra components, and now you might have brake pads. Those brake pads may need to be maintained. And there's still a little bit of extra electronics, but not as much. But you need extra electronics to actually control that mechanical brake. So a brake resistor is a common way that's relatively low cost straightforward to implement, and it's a way of making sure that the system slows down faster than it would if you just left it to it. Now, standard VFDs are divided into two main types. We get constant torque versus variable torque, or CT versus VT. Constant torque is used where the torque is constant throughout the speed range. This is very good for loads that are harder to start and have a higher starting current. Also for loads which have dynamic performance. It could be cyclic operations, alternating loads, discontinuous motion. So examples of that include conveyors, crushers, extruders, positive displacement or gear pumps, centrifuges, mills, mixers. And what you have there is inside the CT, you have a high performance 1 minute overload capacity, which protects against load spikes. So with a standard CT type VFD, you'll get at least 150% over torque for up to 1 minute. And in some VFDs, that could be up to 200%. So it gives you the capability to control these hard to start loads, and also it gives you very good performance on dynamic loads or applications which need dynamic performance. Now there's a downside, of course. A CT VFD, because it's got this higher performance, it does cost more. So for many applications, people prefer to use VT or variable torque. With this system, the torque drops as the speed goes up. So this is good for loads which are easy to start with a low starting current. Very good for applications which need constant operation at a standard speed. So that includes things like pumps, radial or axial fans, because these devices, typically you turn the fan or the pump on and it just runs at the same load without changing. And also, you're not too worried about how long it takes to start up because it's running continuously. So once it's running, it's quite easy to keep going, but also it has a relatively low starting current. If you think about a fan, for example, the only resistance you've got in starting a fan is the inertia of the actual fan itself, and then whatever air pressure there is, but generally that's a lot lower compared to starting a conveyor or some other big mechanical device. Now, applications rarely exceed the rated current, so a VT often only needs about 110 to 120% 1 minute overload capacity. So that means that the VT can be a lot smaller and it can be lower cost compared to the equivalent CT. You could use a CT VFD on a VT application, but it will be overspecified and cost more. Potentially you could use a smaller frame size of a CT VFD and then match the VT application. But in my experience, even if you go down the frame size, you'll still be paying more for the CT VFD compared to equivalent VT VFD. So variable torque is very good for these simpler applications. CT has its place. If you're not sure, use a CT, but if you've got the wrong type of application, it will be overspecified and it will cost you quite a lot more to buy. Running costs, not so much. It's normally about that startup cost. And in terms of that difference in price, my experience, a CT VFD is about twice the price of equivalent VT VFD for the same sort of load of motor. So quite a big difference. For accurate control, VFDs often have multiple control modes. The simplest is volts per hertz. So what we do is we control the magnitude of the voltage and the current relationship. This is very good for these VT type applications, good for fans and pumps, maintains full torque range, limited percentage of motor slip, but it may not be able to maintain torque at very slow speeds, but fine for faster items which are running at pretty much constant type applications. For higher starting torque and better speed control, we can get sensorless vector control, very good for these deep well pumps and these high constant torque applications. But of course it costs less, so what you'll find is in a VFD, as you add more of these modes, there's extra electronics, more powerful electronics, it does increase the price. Now you can also have flux vector control. This is open loop. It improves on volts per hertz by providing both magnitude and angle control. So what the VFD does is it senses the motor flux and orientation, and it can provide more precise motor speed and torque control. But again, you need more electronics to do this and bigger control electronics. So this sort of flux vector control does cost more, although it does give you more accuracy of control. And then finally, we could have closed loop vector control. This uses an encoder to provide the shaft position and feed back to the drive. This gives us very good control because we know exactly what speed the motor's going at and we know what all the electrical parameters are. This gives us the best performance and control, but it does cost extra, of course, because you need the encoder, you need the extra encoder electronics, and you also need the extra electronics inside the VFD. But it's ideal for crane and hoist applications. And one reason for that is it does allow full torque at 0 speed. So very good for starting a crane or hoist. Even if they are very heavy and hard to move loads, we can still shift those by using that type of control mode. So if you're not sure, for many applications, it's quite easy to get away with volts per hertz. But what you can do is, as you're tuning the VFD and the application, you can look at these other control modes if they're supported by your VFD in order to improve the control of the motor and the load. Now, I mentioned audible noise coming from variable frequency drives. Variable frequency drives often use fans to cool the electronics. Those fans can be quite noisy, particularly as the VFD gets hot and the fan has to run at full speed. So one possibility there is if you oversize a VFD, then it doesn't get so hot. So that can reduce fan noise because you don't need to use the fan so much to cool it down. Of course, it costs more because you're choosing a bigger VFD. It reduces your efficiency somewhat, so your energy savings aren't quite as good, although that's less of an issue. But it's certainly very good where audible noise is important, particularly around the fan speed. Now, another option we mentioned, VFD electronics themselves also create a switching noise. A typical switching frequency is 4 kilohertz, but with more expensive VFDs, you can often adjust the switching frequency. You may also need to derate the VFD size as well, and that can move the noise to a different frequency. So for example, if you've got a VFD in a commercial application where 4 kilohertz is a problem, what you could do is you could derate the VFD according to the vendor's instructions, and you could move that frequency up to 16 kilohertz. 16 kilohertz is a high frequency and also easily absorbed, and in that case, using that would be effectively inaudible to most adults. Younger children might still hear it though, and there could still be some people who are disturbed by the 16 kilohertz, but that noise wouldn't travel as far and it wouldn't be audible to the majority of people. There is 2 issues there, of course. One is you've got to have a VFD which can cope with the 16 kilohertz. You've got the derating issue, and the other challenge is higher frequencies. Because those frequencies are still going into the motor, but they're not causing motor movement, they do result in losses in the motor windings. So you effectively get more heat inside the motor being generated without any benefit from extra performance for the motor. So there are downsides as well. So you may need to also derate the motor as well as derate the VFD to make sure that additional heat isn't causing any problems. But again, if noise is important, you've got those couple of options there: oversizing the VFD and switching the switching frequency, which often again means oversizing the VFD by derating. Now, I mentioned that AC motors are generally very reliable and don't need much maintenance. There is some standard maintenance which is required. Every 5,000 to 15,000 hours, you're recommended to inspect for dirt, grease, oil, moisture and overheating. When the motor's down, you can also test for problems like insulation deterioration or damaged windings or damaged connections or worn bearings. They can be caused either just through natural wear and tear, but also if there's a lot of vibration or if there is a harsh atmosphere, that can affect the motor as well. The recommendation is to lubricate the bearings and other friction points. You have to use the proper type and amount of lubricant, and your motor vendor will give you guidance on that. If there are any worn or damaged components, they should be replaced. Bearings have a limited life and can often be replaced quite easily. Brushes might also need replacement depending on the type of motor. You should look at motor vibration and attempt to minimize that. So that might be particularly where you've got a motor that's coupled to, say, a gearbox or to another mechanical device. You might want to look at balancing and aligning that coupling to minimize the amount of vibration. Otherwise, each time the motor goes round, it's being forced in different directions, and that vibration can affect the bearings and affect the life of the motor overall. You might also want to look at the voltage, current draw, for speed, for torque and other parameters, just to make sure that the motor is still operating within its required parameters. And then they could potentially, if they're changing, indicate other signs of problems with the motor. And overall, what you're looking at is analysing performance just to see, is the motor about to fail, or is there suboptimal operation? And if there are problems with the motor, you could either replace the motor, or potentially you could get the motor refitted or reconditioned. It is possible to rewind the wirings on the motor. Certainly you can replace bearings, obviously lubrication if it's not well lubricated. So there's a variety of things you can do with the motors there to keep them operating at the optimal performance. In contrast, VFDs need very minimal maintenance. There would be various inspections like before, so typically weekly. You might inspect for dirt, grease, oil, moisture, maybe overheating, insulation deterioration. If there's vibration, that could be causing loose connections, but generally they don't need much maintenance as long as they're kept clean and dry. Now there are fans, so you might need to clean or replace air filters which protect the fans. That will depend on if the VFD has those or not. It could be those filters are actually on the enclosure. If the VFD is inside an enclosure, you don't have fans on the VFD itself, you would actually have those fans on the enclosure. And then annually, you might want to do a thorough clean and inspection of the VFD. For example, you might want to just use some sort of air pressure to clean the vanes of the heat sinks just to make sure they're not clogged up with material. But again, if they're kept clean and dry, that should be a minimal requirement for that. The great thing about a VFD is there are diagnostics. So if anything goes wrong with the VFD, then you can use the front panel display, or you could use the communications, or you could plug in programming and configuration software, and that can be used to find out what happened to the VFD. Is there a failure in the internal electronics? Was there an overvoltage? Was there some other problem? And also with that, you can also keep an eye on things like the power, the voltage, the frequency, power factor, and so on. So all of that can be used as a diagnostic to make sure that the VFD is operating correctly without actually having to go and do that physical maintenance. Again, if it's really kept clean and dry, there's very little requirement to do anything other than just the regular inspections to make sure that nothing's gone wrong. Now it's important to size the motor and the VFD correctly. For motor sizing, typically what you'd be looking at is the amount of power and torque and speed that's required for the application. So that would normally come from a consideration of the mechanics, what sort of devices you're powering. If it's a conveyor, you'd need to consider things like how heavy is the conveyor belt. You'd need to consider how much load is going on to the conveyor, and that would give you your power and torque requirements. Along with the gearbox, you'd need to know what the speed requirements are so you can make sure that the conveyor can operate at its required speed. You might also need to factor in other operating conditions and duty cycle. So do you need a motor that's sealed to IP67, or do you need maybe a motor that's not quite so sealed and operates in more varying conditions? What about the duty cycle? Is the motor operating all day, every day? Maybe it's only operating on a shift basis. Maybe you're only operating it 8 hours a day, 5 days a week. Within that operation parameter, how often is the motor starting and stopping? So normally, what you would do is you choose a motor that meets your requirements. Ideally, you'll choose the smallest motor that meets the operating conditions you have. You could use a larger motor, but a larger motor, first of all, it's uneconomic, but also having too large a motor can cause other problems. So you might find that the motor is overcoming all of the other mechanics. For example, you might be driving a gearbox harder than it can go, so that could cause problems with the actual mechanics. If you're trying to drive a conveyor too quickly, you could end up stretching the belt. So oversizing can be problematic in itself, but the key issue is buying a bigger motor than you need costs more than you need. Another factor there is efficiency. A bigger motor, because it's not operating at its 100% load, it becomes less efficient compared to operating a smaller motor at 100%. So because the majority of the operating costs of a motor are actually the power over its lifetime, choosing a bigger motor, it can be extremely uneconomic, not just because of the extra cost of the motor, but because of the extra cost of having to provide electricity to the motor. Now, once you know how big your motor is, then what you can do is you can either use an ammeter or you could use some sort of modeling techniques, and you could measure the load current under all the different load conditions to find out the peak current that's drawn. What you need to know is you need to know the torque required to start motion. So again, that's going to vary depending what the load is. You need the torque required to bring the load to a speed in a certain amount of time. So how long does it take to ramp up? You need the torque required to keep the load moving. And of course, if it's a VT type application, this is going to be the most important one. You might also need to be concerned with torque required when the motor acts like a brake to slow down the load. That will also help you size your braking resistor. And then you also need to consider what is your peak torque. So torque is related to current, and based on that current, then that's the ideal parameter we use to size the VFD. So what you typically do is look at the maximum current draw at the peak torque levels, add an extra margin, and then that would allow you to choose your VFD. It's generally possible to size a VFD quite accurately to the motor size. You could also look at the VFD and compare it against the motor, and you may say I can actually use a smaller VFD because maybe my peak torque isn't as high as I'm expecting, so that would allow you to reduce the size of your VFD. But you need to be a bit careful there, because if ever things change in the future, then you might need to replace your VFD. Now generally we're looking at current, so amps. Amps is the parameter we should be looking at to size our VFD, but often you don't get the current that you require if you're replacing a legacy VFD, or if you're just looking at the motor nameplate, you might just see a kilowatt rating. So in that case, you could replace the old VFD just based purely on its kilowatt rating, or maybe it's got a horsepower rating. That isn't as accurate as using the current, but it would normally give you a VFD that's good enough. Possibly with modern VFDs, it would be oversized compared to the old VFD, but that's not such a huge problem by oversizing the VFD compared to oversizing the motor. So lots of different ways of calculating what you need, but the key point is it's generally about the maximum current draw, and you would choose your VFD based on that maximum current draw. Again, check your VT type or CT type, because if you've got VT, then that can provide overcurrent for about 110 to 120% per minute. So again, that would allow you to reduce your VFD size if you know that your constant torque is lower. And with a CT type VFD, you've got 150% overload per minute, or sometimes even higher. So again, you might look at the torque required to start the motion. That might be quite high, but once the load is moving, the torque might be reduced. So again, you can size your VFD accordingly based on both the torque required and the current required to keep the load moving, as well as what's required to start up. Newer VFDs tend to be better for that, and paying more money for a VFD will give you better characteristics. But of course, you don't want to spend too much on your VFD. But again, another possibility is specifying a slightly smaller VFD, as long as it's got the correct startup characteristics. That could also help save money, because you could go down the frame size on the VFD but still get the performance you need. Now, many applications have some sort of coupling. The most common sort of coupling is a sort of gearbox. A gearbox is used to change speed and torque. A related sort of coupling might be like a belt drive, where you've got different size wheels on the belt, but a gearbox is more common. Now, a gearbox, it can be used to change the speed and torque. Typically what you do is you have a reduction gearbox, which is used to reduce the speed, and that increases torque. And there's a direct relationship there. So if you've got a 1-to-2 type gearbox, it would reduce the speed by 50%, but it would double the torque. So a very simple ratio for the gearbox. Sometimes it's not quite as straightforward as that. There might be a few losses in the gearbox, but normally they're minor. So generally, it's a straightforward ratio of reduction in speed and increasing the torque. You can do it the other way, but that's rare. You can use it to reduce the torque and increase the speed. But there are problems with doing that. First of all, you have to consider, can my device actually cope with the speed I require? If you're putting in a high speed to an increased speed gearbox, potentially your output of speed could be so high you could actually destroy the gearbox due to the mechanical forces. So reduction gearboxes tend to be a lot more common and also a lot more useful. You think about a typical motor that might be running at 3,600 RPM. It's rare to need that full 3,600 RPM. So reduction gearbox will allow you to reduce that speed, but correspondingly increase the torque. So this can also affect your motor sizing, of course. By knowing what your speed and torque is, then choosing an appropriate gearbox, that would allow you to choose a smaller motor potentially, but still get the required torque you need by using a higher speed motor and then the reduction gearbox. Gearboxes do have their issues. A couple of main issues. You have to think about backlash. When the gearbox changes direction, then because of the way the teeth interact, then you have to reverse, and there's a slight movement before the teeth engage in the opposite direction. That's called backlash. And the gearbox also adds a load in itself. There is some additional inertia and there is some additional friction inside the gearbox, but normally that's minimal compared to the overall final load. So you've got your VFD, you've got your motor, something goes wrong. So there are various ways to fault find on the VFD. Typically a VFD has a status on its front panel, and by referring to the user's manuals, you can see what that status means. So maybe the emergency stop was applied, maybe there was an over temperature, maybe there was an overcurrent, maybe there was an unbalanced supply, maybe there's a problem with the system on the motor, maybe there's a configuration issue. Of course, what you can also do is you can check that power is applied, you can check that the voltages are okay, and you can do that using a standard multimeter. You might also need to check the actual installation. Cables and accessories might need checking. For example, the chokes and the brake resistors in particular, they may have shorted or overloaded and burnt out. Of course, check the mechanical part as well. You're checking for jams or overloads or blockages. One important point is with VFDs, they do contain very high voltages internally. It's not recommended that you start taking the cover off a VFD and fault finding inside. That's normally a specialist function. And because of the way the voltages are chopped up and the way capacitors are used for doing that, those high voltages can remain for several hours or even longer after the power is removed from a VFD. So be very careful when you're doing anything that's actually inside the VFD itself, and best left completely alone, because those voltages are very, very high. And they're also DC voltages. DC voltages are particularly problematic because with an AC voltage, you might still be able to get an electric shock and move away. But with a VFD and the DC voltages, all your muscles, if you get an electric shock, are sort of locked in place, and then you can't release yourself. So that means that once you get that high voltage shock, you're stuck to it until you get a very high level of injury and die, or until someone turns the power off or levers you off, hopefully using some sort of wooden implement so that they don't get an electric shock themselves. So be cautious, very high voltages, be very, very careful around VFDs. Here's a brake resistor calculation guide. There's no simple formula because different resistor values affect the application in a relatively linear way. So lower resistor values result in a shorter braking time but need higher power. Higher resistor values, they result in longer braking time but lower power. So you can adjust the resistor values based on the requirements for your application. You've got to be careful. If the resistor value is too low, then that could effectively cause a short circuit on the VFD, and that could cause the VFD to stop, and then the motor will just coast to a stop. So if your resistor value is very low, that's an issue. But you can do some calculations based on these formulas we got here. So there's two parameters to a resistor you need to calculate. We need to calculate the resistance value, and then we need to calculate the power value. So for resistance value, that's typically the switch on voltage squared times, or divided by rather, a combination of the motor power times the motor torque times efficiency. So switch on voltage, if you don't know what that is, you can look at the RMS voltage of the output times 1.35 times 1.25. That gives you the switch on voltage. You can then look at motor power. Typically you'd use the rated motor power of the motor, but you could use the VFD power if you don't know. Torque is typically 100 to 2% of rated torque. If you're not sure, you could use a value of 1.5. Motor efficiency varies between 80% and 98%, so your value here can be 0.8 to 0.98, but if you're not sure, you could use 0.95. And then you also need to calculate the drive efficiency, so that's 0.9 to 0.98 or 0.95 if unknown. So as an example here, if you've got a 230 volt 2.2 kilowatt VFD, then your resistance value, by doing all those calculations, it comes out at 51 ohms. Now that's quite a low value for a resistor. So we also need to calculate the power value, because we're going to need to know how much power that resistor is going to dissipate. If we get the power too small, then the resistor will just be destroyed in a small time. If we get the power too big, then that's less of an issue, except for it means it's a bigger unit and it costs more. So to calculate power, we look at motor power times the maximum torque times the duty cycle. So you can start off with motor power using the rated motor power, or the VFD power if you don't know. You look at the maximum torque again, so same as before, 100 to 200% of rated torque, or you can estimate 1.5 if unknown. And then you can look at the duty cycle, which is the ratio of time when the brake circuit is activated. And this varies a lot. You know, for a hoist or a lift, then half the time it's going up, half the time it's going down, so that's a 50% duty cycle. If you've got something like a pump or a fan that's running continuously, then the duty cycle might be a lot shorter, and you could select, say, 5%. So for example, we've got a 2.2 kilowatt drive, same as we've got before. It's got a 40% duty cycle. We know the power is 2,200, that's 2.2 kilowatts. We estimate 1.5 for the maximum torque. We know what the duty cycle is, 40%. So doing that calculation, your resistor needs to be 1,320 watts. And that's a pretty chunky resistor, but you know, for this application, that's what you'd use. You could use a smaller resistor, and that would give you a shorter braking time, but then you'd need to up the power, because likely the power would go up. You could use a higher resistor value, that would give you a longer braking time, but it would reduce the amount of power you need. So you could trade that off by adapting the duty cycle and by adapting some of these parameters. But this is a good estimate for calculating that brake resistor. When people talk about motors, they often talk about torque, horsepower and power. So I've just got a few notes here on how those are related. So torque is a force that produces rotation. That's commonly measured in Newton meters. So that's a sort of rotational energy that you need. Whereas if you look at horsepower, or HP, horsepower is torque with the addition of time and distance. So for example, you can take the torque generated to move something a given distance in a given time. So for horsepower, you typically calculate torque times speed divided by this constant, which is 5,252. The final one here is power. Power is the rate at which electrical energy is transferred by an electrical circuit, and that's calculated in watts or kilowatts. And quite simply, horsepower is watts times 745.7, or of course you could rearrange that circuit. If you knew the horsepower and wanted watts, you could get there. But quite simply, 1 horsepower is about 746 watts. So if you need to do any calculations across those 3 different types, that's how you can calculate it. Torque calculations, they can be quite complicated. Normally with motors and so on, we normally start off by knowing what the horsepower or the kilowatts is, so that generally makes it a lot easier. But if you do need to, you've got the calculation there, so you can work out torque as well using that parameter 5252, which is the fixed constant to convert from horsepower with speed using torque. Now another factor that's important with motors is power factor, or also known as cos phi. This is the ratio of real to apparent power, and it reflects the offset between the current and voltage measured between 0 and 1, where 1 is best. So if you think about an AC voltage, you've got your AC supply, you'll have a reading of the AC voltage, and the voltage would be at one level, and then you'd have a reading of your AC current, and if they were at 1, then they would be totally coinciding, and that would mean that you've got a very good power factor. You've got a combination of the current and the voltage, they combine. But what happens with motors is, because they're non-linear loads, they can affect power factor, and so can VFDs. So what you'll find is the current becomes offset from the voltage cycle, and that can cause problems on your power supply. It can be corrected because you can add either absorbing reactive power, you can do it with capacitors or inductors, and you can also supply reactive power as well, and you can maybe offset different types of motor with each other to offset the different loads there. Crossfire, generally for the motor, it depends on the motor size. Larger motors at higher loads are the best. So an unloaded motor has a very poor power factor of only 0.15 to 0.2. At half load, that increases to 0.7 or 0.8. And then really at full load, that's where you get the best response. It's between 0.85 and 0.9. So power factor, it's important because what it means is you're effectively wasting power. And it's also a problem for the generator companies, because the generator companies, they want to supply power factor at a ratio of 1 where the current combines with the voltage, because that's what they need for their generating equipment, and it's also what you need for the distribution equipment. Otherwise, if you have lower than 1, you can cause heating in the power transition wires, and that leads to extra losses, and it costs money and can cause failures. So the power generators want as close to 1 as possible, but in practice you can't necessarily achieve that. So what you might need is you might need to apply that correction on your site by performing some sort of corrective work, adding capacitors or inductors to supply or absorb reactive power, by offsetting reactive loads in one direction against reactive loads in another direction. But also this is why we want to choose the VFDs and the motor to be as close to the required load as possible, because the closer they are to the full load, then the less power factor correction we have to do. So power factor is important from a cost and efficiency point of view, often neglected until your energy company increases your bill because they tell you your power factor is very poor. So as soon as you get that increased cost from your power generator, then of course you'll be looking at improving your power factor, and there's various ways of doing that. So we'll finish off with some terminology. AC is alternating current, typically measured as a voltage, which is the RMS value. RMS is 0.7 of the peak value. Current, measured in amperes, this is the rating of the power supply and may also refer to the amount of current flowing through a cable. What we're actually measuring is the amount of electron flow. DC is direct current. There is DC inside the VFD. We convert AC to DC, and then we can convert the DC back to AC again. So that's the function of the VFD, to do that conversion. And the reason for doing that conversion is so we can change the frequency of the output. Now we've got diodes. Diode is an electronic device that restricts current flow in one direction. There are diodes inside the VFD, but more likely there are more complex semiconductor devices. But diodes can also be used in a bridge rectifier, and that's a device that converts EV AC power to DC power. Earth or ground. This is our connection to the ground. Literally, there is a connection to the earth. There is a spike which is buried into the ground somewhere, and this is used for safety purposes, and it can also be used on cables to reduce electrical noise. So in Europe, there's generally a requirement that any VFD motor is shielded, and that shield is connected to ground at one end in order to reduce the amount of noise generated by the cable when it's driving a motor. Frequency, this is the number of cycles per second for AC voltages measured in hertz, typically 50 in Europe and 60 in the USA. Fuse, this is a device to stop power delivery when the current limit is exceeded. Normally with a fuse, this is a device which uses a piece of wire rated to melt when it gets to a certain temperature, and the temperature is related to the current going through the fuse. So it's a destructive device. Once the fuse is blown, it has to be thrown away and replaced. There are also options for MCBs, miniature circuit breakers, or MCCBs, molded case circuit breakers, or just CBs, circuit breakers. They can also be used for protection as an alternative to fuses. Going back a bit, we have horsepower. Horsepower is torque with the addition of time and distance, generally measured as the amount of torque generated to move something a given distance in a given period of time. Positive, this is a wire supplying current. Nominal, this is the rated amount. The actual amount may be higher or lower, but normally not by very much. If we talk about a nominal, for example, a nominal 230 volt supply, then the minimum could be as low as about 220, the maximum could be about 240, but the nominal would be 230 volts. Same with current or power on the output of a VFD. We have a nominal rating, for example 2.2 kilowatts. The actual rating may be higher for short periods for an overload condition, but the nominal continuous power would still be that 2.2 kilowatts, give or take a very small amount. Power, this is the rate at which electrical energy is transferred by an electric circuit, measured in watts or kilowatts, or maybe even megawatts in very large systems. PSU, that's a power supply unit. Resistance, this is the measure of opposition to the flow of electricity, measured in ohms. This is something that has a place in VFD applications. For example, the motor cable will have some resistance, the motor windings will have some resistance, but generally the resistance should be very low. Yeah, we're more concerned about reactive aspects because we're operating at AC frequencies. If you just try and measure a DC value on a wire, that's very good to test continuity, but it doesn't really tell you much about the system. Same with resistance on the motor. If you measured the motor coils, you should get a very low resistance at DC using a standard meter because they're really designed to generate power using AC electricity. But a good way of measuring if the wire is damaged or if the motor winding is damaged, you can use the resistance and you can just measure using a resistance meter. And if you get a very high resistance, that indicates maybe damage or open circuit. You should be looking for a low resistance. Root mean square, RMS, that's what we do to convert the actual voltage we're measuring with a standard meter into the peak voltage. 0 volts or return, also indicated sometimes as minus. This is a wire carrying return current back to source. That could also be a neutral wire in a three-phase system. And we saw that with star delta. With a star system, you have a wire in the middle. But with most VFD applications, we normally assume they're balanced. If they're not balanced, you would use like a reactor to improve the balance. But with most VFD applications, you just have the 3 wires and they're wired in a delta arrangement. Torque is a force that produces rotation, commonly measured in Newton meters, and there is a conversion we can use to calculate from torque to get to kilowatts and get to horsepower if we need it. Transistor is an electronic device that switches a large current from a smaller one. We do have a sort of transistor inside a VFD, but it's more of a different type of device related to a transistor. But that device is used to chop up the DC supply into a pseudo AC current. And that's one of the key components of the VFD. It's these electronic devices which do that switching of the power, and they result in your output, which you use to control the motor. VFD, that stands for variable frequency drive, also known as variable speed drive or VSD, also known as inverter, also known just as drive, and there are other names as well, but we use the term VFD, variable frequency drive, because that's what it's doing. It's varying the frequency to the output of the drive to control the motor speed. And the final one there, voltage. Voltage is the pressure from the power source to push the current through the system. Higher voltage means higher pressure. And that's also related to current and related to power itself. But voltage is important because that's what we use, and we have to rate the VFD according to the voltage of the motor and the supply current. And we also need to take care of high voltages because high voltages can be dangerous.